Now listen to this. You take any particular mechanism like E2. In E2, what is happening? There is one group leaving from here. At the same time, base is trying to extract the proton. These two will happen simultaneously, and that's how we will get a double. This is the basic idea of E2 mechanism. Now for this reaction, if at all I calculate the rate would be equal to some constant K into concentration of the alkyl halide, Rx. Okay, alkyl halide into base. Correct. Now, only without changing the concentration, structurally, if at all I change this as CD3, CD, CDD, and CD3 here, and H and D. So basically all hydrogens are replaced by deuterium. And then again I do the elimination. When I do the elimination here, then I would get CH3 and isotopic double bond. The only difference between these two is isotopic. This is CD3, this is CD3. And now if I calculate the rate would be equal to some K into Rx into B index. Since the concentration is same, base concentration is same, the only thing that varies is this and this. Okay. So if there is any difference in the rate that is coming, let me call this as R1, this is R2. R1 by R2 will be equal to KH by KD. Students, and this ratio is found to be different for different mechanisms. Yeah. For example, if at all I take KH by KD, the ratio is found to be greater than almost between 4 to 8 if you are able to find it. If this is the ratio which we are able to find it, right, then we say the mechanism is going through primary isotopic effect, which means this can only be possible when your carbon hydrogen bond or carbon deuterium bond is breaking in the slow step. In case of E2 mechanism, this itself is a slow step. So this would happen only when you have this. Is this clear, everyone? Okay. This is about primary isotopic effect. Secondary means, suppose if there is a reaction like E1 or SN1, like we have this one, halide, and in this mechanism, this is a slow step where we first get a carbocation and X minus is later. But during this mechanism, in the slow step, there is no carbon-hydrogen bond breaking. So if carbon-hydrogen bond is not breaking during the slow step, we usually find KH by KD, less than that of 2. So the value in the change in the rate would be very less. Then we say this mechanism is going through secondary isotopic effect. Another term you're asking me was regioselectivity and stereoselectivity. Suppose if there is X here, halide here, and after elimination, I'm able to get these two. Correct? Now, if both of them comes 50-50%, both of them comes 50-50%, then I'll say there is no selectivity for the base. Base can equally approach here, base can equally approach here, and both the products are coming. Then we say it is a non-regioselective product. None of them has been selective. But on the other hand, if the same thing has come out to be, let's say 90, this has come out to be 10%, and this has come out to be 90% as the final product, then we say mechanism is very choosy. That means base is very choosy that most of the time it is attacking here only. That's why the product we are getting is what we call it as regioselective. So this is a regioselective, and same way if you look out here, since the base is approaching this most as compared to that of this. This direction on which it is attacking is called regiospecific. This is regiospecific. So I guess you understood the difference. What is regiospecific and regioselective? Let us start with the mechanism. Let us start with E1 today. So I want all of you to keep writing along with me. In E1 mechanism, what we expect that alkyl halides undergo E1 mechanism when solvent acts as the base. Solvent itself will act as a base. Example, if you have chlorine, heating, OH and heat. This is how it is. And if you get this, then we say it is following E1 mechanism. Let's see what is happening in the mechanism here. Chlorine. In this slow step, there is a carbocation formation and Cl- is lost. This is step 1. And after the formation of carbocation, PTOH as a base is extracting a proton from the beta position. And as it extracts, double bond is formed here. Double bond plus PTOH2 plus, and which both of these react to form PTOH2 plus Cl minus, eventually form PTOH plus HCl. The second step is the fast step. Now this is what we expect when we have E2 mechanism. So all of you understood this point. Now usually we know that this is a very weak base, ETOH. But when you have complete solvent, this ETOH itself is a solvent. So solvent is so much amount, the quantity wise it is so big as compared to that of substrate, that it will make this reaction to happen and get this double bond. Yeah. If you see the reactivity will be tertiary greater than secondary greater than primary, which comes with the fact it has to do with the stability of carbocation. And similarly, if you check out RF, RCl, RBr, and Rn, if there are different halides, the reactivity depends upon the bond dissociation energy. The biggest difference between E1 and E2 is the base concentration. If your base is very strong, then it would usually try to go for E2. If the base is weak, like solvent, ETOH is a very weak base. So it will let the carbocation form first. Moreover, the solvent has to be polar, because this polar solvent can only make this molecule to split into positive and negative charges, just like water. Water can make this to separate. Similarly, this ethanol will make them to separate only. Here we go. Next is the regioselectivity of ethanol. Suppose I have chlorine here, treat that with PTOH. Then I can get this as major and this as minor. But if you see through the mechanism how it goes, so from here, let's say it has started as a reactant and it will reach to this point, some intermediate which is carbocation. So from here it might reach to this point or might reach to this point. Now Till this part it is carbocation formation. Here it is RH. Okay. This is the second step where from carbocation it is forming an alkene. Now if you observe the same question, this will be the alkene which is forming here. This will be the alkene which is forming here. Right. Let me call this as product P1, product P2. So this is P1, this is P2. Going through a transition state 2, transition state 1, and transition state 2. Got it? So why E1 shows regioselectivity? See, up till carbocation formation, mechanism is same, but the second step is the one which decides, which product is going to come most. So in the second product, the one which is more stable, that would have less transition state. So which has more chances to get into the product formation? P1. I guess all of you understood that. So that's why if it is major product asked, then more substituted will be major, this will be minor. Here on this. So yes, when it comes to E1, E1 also shows regioselectivity, just like E2. Okay. Now this is a two-step reaction, right? From reactant, first an intermediate is forming, this one. And from intermediate, then the product is forming. That is how the E1 mechanism happens. So from reactant, first an intermediate is forming. And from intermediate, again it has to get through product, which means it has to go through the second step now, where base will come, extract the proton. So momentarily energy will increase before it becomes an alkene. Between these two, transition state will always be between one step. Between these two, there are two. Between these two, there is one. Alright. So this transition state describe more about the slow step, because you can see the activation energy required here is huge. Now look over this. Suppose if you come across this molecule, and we know that the major product which you will get is this one. But within this, we can have cis and trans also, right? Within major, I can have cis and trans as well. Now between that also, major product will be trans, only because of the energy difference. So which means, suppose if this is where the E1 is starting, it comes to an intermediate here. So from an intermediate, it is able to go to this molecule, or it is able to go to this molecule. Sorry. And let me write this as minor P1 and P2. So which one will be P1 beta here? This one is P1, this one is P2. So within the major also, you would observe which side does it go. It will go towards the trans side. Clear, everybody? So yes, it is regioselective as well as stereoselective also. So even mechanism is regioselective because it is choosing more stable double bond. Then and stereoselective as well. So therefore, given any molecule, we must be able to choose which is going to be major product. E1 is definitely an regioselective and stereoselective mechanism. Let me show you with a question here. Suppose if this is how the reactant is, they take ETOH and heat. What is the first thing you will do in these cases? Make sure you make a carbocation. So if you make a carbocation, where does that form? Here is the carbocation formation. So from here the products would be. And we have always learned that carbocation undergoes rearrangement because this is at secondary position. If at all I make a methyl shift, so 1, 2, methyl shift, we can get a more stable carbocation. This way I can get more stable carbocation. So from here, the elimination will happen. So I can get two products here, one with double bond here, plus one with double bond here. These are the two products I can get. Another product which I can get is before the rearrangement itself. So before any rearrangement happens, here there is a beta hydrogen, beta carbon and beta hydrogen. From there the double bond can form. So these three products can be formed. Well, here there are no cis and trans, but if that is also the case, then you will have more number of products. So first thing, if a question is asked, how many number of products are formed, you have to write all the possible products in E1, wherever before rearrangement and after rearrangement. Okay, students, which one will be the major product here? Clear on that, everybody? So if you see, this is 1, 2, and 3. Okay, got it? So stability wise, which is more stable beta? 3 is more stable than 2 is more stable. 1. That's why third one is major. So I hope you understood how to do E1 mechanism now. Another important question on the same lines. Suppose if I am taking ETO minus and K plus. ETO minus and K plus is a completely E2 mechanism conditions, because E2 mechanisms require a strong base. If it requires a strong base, it will extract proton from here, or it try to extract the proton from here, but there is no proton here. Check out the position, everyone. This is alpha position, this is beta position, and on beta position there is no hydrogen. So although it is an E2 condition, write down this is E2 condition. Okay. There is no alpha, there is no beta hydrogen here. No beta hydrogen. So we won't say reaction is not happening. We would say reaction is not happening via E2 mechanism. So since there is no other alternative, it has to go through E1 mechanism. So how does the mechanism go now? So carbocation will be formed here. Rearrangement will take place this way, carbocation, and then elimination will take place. So ETO minus make an elimination, will get two products. So just mention that when there is no scope of E2 due to absence of beta hydrogen, if we have Cl here, let's treat that with ETOH, so I can get this double bond here, and this can go via E1 mechanism. Even if you take ETO minus and heat, first one was an E1 condition, second one is an E2 condition. Here also you can have the same double bond. You know that I'm writing only major products. Endo bonds are more stable than exo bonds. That's why both by E1 and E2 mechanism, E1 CB as in elimination, unimolecular conjugate base mechanism. Now let's see what is the condition. Suppose if there is any Z group that is connected to CH2, and X. Okay, and that when you treat with ETO minus and K plus, and heat. Then the product will be ZCH double bond CH2. This is the product formation. The condition here is uh, this beta hydrogen must be acidic, which means this Z must be some strong withdrawing group. It must be some strong withdrawing group. And at the same time, this X which is leaving, right? This should be a poor leaving group. Poor leaving group. Poor leaving group as in which are strong conjugate bases. For example, F minus, OR minus, OH minus, NH2 minus. They don't leave very easily, right? These groups are very poor leaving group. Yes, students. So, which means what kind of a Z group we are expecting here? There should be strongly electron withdrawing group. That could be by NO2, like C double bond O CH3, like CHO, like cyanide, and so on. So strongly electron withdrawing group. It's not over beta. First we have to go through or get an overview of all the mechanisms, then we'll stick on to one cases. Okay. So I'll have to read, because when you have dehydration, okay, a lot of reactions will again come back of E1. All right, just keep patience. First, let us learn all the types of mechanisms. Okay, beta. Next, Z connected to CH2X, and let's say there is H here. Base ETO minus is trying to extract proton from here. As soon as it extracts proton, this carbon will become carb anion. And this is going to be usually a fast mechanism, fast step. So this will have ZCH minus and CH2X. And from here, this step is relatively slow, where the minus charge is trying to make a double bond and X minus is leaving. So this is the slow step of the reaction. And that's how we'll get ZCH double bond CH2. So rate of the reaction, if you observe, rate depends upon some rate constant K, and you have to check out the slow step. So you can see this is the slow step. So in the slow step, there is only one of this intermediate, that is ZCH CH2X minus. This is the intermediate which you have. In chemical kinetics, you will learn one thing. Suppose if there is a reaction A, it is giving, let's say A plus B is giving an intermediate C, and C is finally giving D, and this is slow step. This is slow step. Here there is some equilibrium existing. In that case, rate can be written as some constant into C, because rate is always written for slow step. But C is an intermediate. Rate reaction should always be in terms of reactants, not in terms of intermediates. So what we can do, we can use this information of equilibrium. So we will take this as K equilibrium is equal to concentration of C by concentration of A into concentration of B. So from here we can evaluate concentration of C is equal to K equilibrium into concentration of A into B. So if I resubstitute that back here, then rate would be equal to some K into K equilibrium into concentration of A into concentration of B. So now the rate equation is completely in terms of reactants. Here everyone. So the same technique I'll apply here. So first I'll assume there is some equilibrium here. So if I write that equilibrium constant, that will be equal to ZCH CH2X with minus that divided by ZCH2 CH2X multiplied by ETO minus. These are the two reactants which you have. This is one reactant, this is one reactant. Okay. So now I can write rate is equal to K into Instead of this, I can substitute K equilibrium into this. So we can write it as K EQ multiplied by ETO minus concentration multiplied by Z CH2 X concentration. Got it? So which is equal to some constant K dash into substrate concentration into base concentration. And you see both of them have 1, so order of this reaction will be 2. So it is a second order. And if you see in the slow step, how many number of molecules are involved? There is only one molecule involved in the slow step. That's why it is called E1. Okay, that is called it is E1. But if you see that E1 is forming because of the conjugate base, hence the mechanism is called as E1 CB mechanism. Okay, that one is always about the molecule used in slow step. Okay, students, please make a note. And all of you, let us try these 3 questions. See, hint is first you see whether it is a weak leaving group or not. This is the first hint you should search in the questions. Second, if there is a weak leaving group, along with that, at this is an alpha position, this is a beta position, and look out always at the gamma position. Is there any strong withdrawing group on gamma position or not? See how it is. In case if there is a carb anion forming, which is what happens in the first step, correct? So this carb anion can undergo resonance stabilization here. And that's why this particular carbon, this is like a methylene carbon. Okay. So this methylene hydrogen is more acidic. So this reaction would happen where carb anion is forming first. Clear everyone? So once the carb anion is formed, in the second step, because you are providing sufficient heat and OH minus is a leaving group, slowly that molecule would leave and double bond can be formed here. That will be the final product. Okay, students. So similarly, what will be the next product here? pH double bond this way. Here also O2, N and double bond this way. These are the product formations. Now if you see E1CB exhibits solvent isotopic effect. First, all of you write these 3 examples, then I'll explain what is solvent isotopic effect. Done all of you? Let us try these 3 questions. See, hint is first you see whether it is a weak leaving group or not. This is the first hint you should search in the questions. Second, if there is a weak leaving group, along with that, at this is an alpha position, this is a beta position, and look out always at the gamma position. Is there any strong withdrawing group on gamma position or not? See how it is. In case if there is a carb anion forming, which is what happens in the first step, correct? So this carb anion can undergo resonance stabilization here. And that's why this particular carbon, this is like a methylene carbon. Okay. So this methylene hydrogen is more acidic. So this reaction would happen where carb anion is forming first. Clear everyone? So once the carb anion is formed, in the second step, because you are providing sufficient heat and OH minus is a leaving group, slowly that molecule would leave and double bond can be formed here. That will be the final product. Okay, students. So similarly, what will be the next product here? pH double bond this way. Here also O2, N and double bond this way. These are the product formations. So I was telling you about solvent isotopic effect. Basically, if you take this molecule and let's say treat that with ETO minus, let's see an equilibrium is established with pH CH2 CH minus CH2F. This is the equilibrium which is established plus ETOH. Okay. Now, what I'm doing here in this reaction, just let me write it as an overall reaction first. So, in this overall reaction, what we are taking ETO minus, and the solvent is ETOD, ethanol, which contains deuterium. In that case, the product what we are expecting would be pH CH double bond CH2, this will come, plus pH CD double bond CH2. Both these products can come, and usually this would be major. Second one would be usually major. Now how this product is coming, let's see. First imagine this step where base is extracting the proton. So it has extracted proton from here. We got a conjugate base. And second step is when you have pH CH minus CH2F plus EDOT, which means being a conjugate base, this also has an ability to extract proton from solvent. So as it extracts proton from solvent, so we will get pH CHD with CH2F plus ETOD minus. And again this reaction which is happening, pH CHD, right, here CD, CDH and CH2F, this will treat with ETO minus, okay, and it could extract this proton. We can have pH CD minus and CH2F, and once you have this pH CD minus and CH2F, this is a slow step where fluorine will leave, and you will get the product pH CD double bond CH2. What I meant to say is, directly without interacting with solvent, we may get the product also, which will be this one. But since solvent is a huge quantity, the anion which is forming may first again interact with the solvent to form this molecule. Once you get this deuterium substituted, then again EDOT might attack and remove this H. Alright. So this time the product which you are getting will also have D in it. Right. So this is a difference we need to make out. So this is a D here, this is a H here. When you have a solvent which contains deuterium, there is most likely an exchange of hydrogen takes place. This is called solvent isotopic effect. So whenever you come across this question, make sure both the products you have to write, and with D will be the major product. Now look over the examples. Suppose, be careful while solving with this. There is a Br here, correct, and double bond O here, and I am taking ETO minus K plus. I want you to write the product and specify the mechanism. What is the best mechanism it can go through? F double bond O. Everyone keep doing it. Let's say this is ETO minus K plus and heat. And similarly, you have Br here, double bond O. Now let's see the first one. First one, how do we decide? We will see this is a strong base. See the way I decide. First, I'll think of basic character, strong base. Right. Second, I'll think living group. Living is a good living group. It's a good living group. Strong base, good living group. Always favor E2 mechanism. So what would this be? We going through an E2 mechanism. So E2 means just adjacent to that bromine, you'll get a double bond. Fluorine. If you remove fluorine from here, it's a weak leaving group. And at the gamma position, there is a helping group here, double bond O, which can stabilize the carb anion forming. So it will definitely go through E1CB mechanism. So double bond O. It is an E2 mechanism. It is an E1CB mechanism. Next one. Tell me. This is an acidic hydrogen. Double bond O is there. Does it go for E1 or E2 or E1CB?
Sir, E2, sir.
Very good. It is E2 because it is a good leaving group. E1CB is highly conditional. It has to have a weak leaving group. So it will go through E2 mechanism only. This is what it forms. There is no
Sir,
beta hydrogen. So what direction it will choose beta? It will go through E1 mechanism. Okay. So first a carbocation will form here. Right? This is what happens. You see, first a carbocation is going to form here. Then carbocation will undergo ring expansion. From here it will break, it will undergo ring expansion. This is where you will have. Then this carbocation which we got, okay, here the carbocation which we got will then undergo elimination. So this is the final product which will be, and it is driven by E1 mechanism. OH minus, very weak leaving group. Cn is a strong withdrawing group. Here there is a hydrogen present. Sorry, here there is a hydrogen present at beta position. Yeah. So yes, it can go for E1CB mechanism. Now let's see next one, dehydrohalogenation. Dehydrohalogenation of dehalogenation, not dehydrogenation. Dehalogenation of
Sir,
dihalides. Yes, please.
sir, how can we say that OH is a poor leaving group?
OH minus is a very strong base. Right, beta? Would it want to come out of the molecule? No, right? Just remember it this way. All weak bases are good leaving group. All strong bases are poor leaving group. Okay?
Okay, sir.
RCHCl2. When you have both chlorines on the same carbon, it is called geminal dihalides. You can see these are geminal dihalides. Geminal dihalides in the presence of sodium and ether or magnesium and ether or zinc. Right. So in all of these cases, it will form RCH double bond CH and R. It is like two radicals RCH. Right. First radical is forming, another RCH CHL is forming R. First, these two will try to terminate. So we'll get CH, CH, Cl, Cl and R. Got it? And again with sodium and ether would happen. Second time also radical termination will happen because both the places there is radical forming. They'll terminate to form RCH double bond CHR. That's how you will get the product. Also known as Wick or vicinal dihalides. So we'll see RCH, Cl, CH, Cl, and R. When you treat that with zinc or magnesium or NaI acetone, it would give us RCH double bond CH and R. This is the product that is going to form. See the mechanism. Mechanism always driven through E2 kind. If I take the Sawhorse projection here, One halide is here, one halide is here. Zinc, lone pair, extracting proton from here, taking it to form double bond, leaving X simultaneously. So we will get double bond like this, plus Zn X2. Think the same lines, but the mechanism of the other part, which is I minus. So think that I minus is extracting X. This pi bond is moving here, and X will come out. So what is the product formed here now? We have Ix plus X minus. It's the product function. NaI is more soluble than NaBr, then NaCl. NaCl will be the least soluble. So whatever X minus that comes here, so the next one we have Br, pH, methyl and methyl. I'm treating that with zinc. Always remember that we have been learning that cis with anti-elimination will give you 3O. Right? So we'll get this as 3O. Okay. And if you do the reverse way here, right? Suppose if you have trans with anti-elimination will give you erythro. This is something we have learned earlier. Imagine the same thing happen in the reverse direction now. 3O, if it undergoes anti-elimination, will give you cis product. Erythro, if it undergoes anti-elimination, will give you trans product. So this is an erythro or 3O here. This is erythro. When you treat that with zinc and heat, what do we get here? We will get trans product. pH, this with double bond, pH, methyl and methyl. Correct? So this is the product which you will get. If we take, let's say, Br, H, D and D here, and I'm treating that with zinc dust. What is this beta? This is 3O. 3O, if it undergoes anti-elimination, what is the product we should get?
Cis.
Cis. So double bond C, D and D, H and H. So that is a major product.
Sir, why we are using zinc dust, sir? The dust.
Zinc is going to provide electrons. Okay. More powdered form, more surface area it can occupy. Okay. So zinc can occupy more surface area, which means it can easily attack on the groups where it has to remove this bromine. So instead of metal, always dust is favored. So first generic thing what you need to write down is that if you have OH here and H here and an elimination is happening, preferably it is because of some dehydrating agent, because ultimately what is the reaction happening? H and OH are being losing. So which means it has to be through an dehydrating agent like concentrated H2SO4, a very good dehydrating agent, or concentrated H3PO4, concentrated anhydrous P4O10, or Al2O3, or Al2O3 with pyridine, Py as in pyridine, or thorium dioxide, or BF3. All of these are good dehydrating agents. Wherever you find these compounds in front of alcohols, there is a high chance they will undergo elimination. Now see the reactivity. So when it comes to reactivity, it is tertiary greater than secondary greater than primary. Right? Which means third degree alcohol, if it is there, it is easy to remove as compared to second degree or 1 degree. Okay. See, when it comes to 1 degree alcohols, 1 degree alcohols like CH3, CH2OH, in case if there is any elimination happening, usually it is preferred by E2 mechanism. E2 mechanism. But if it is 2 degree alcohols or 3 degree alcohols, 2 degree alcohols or 3 degree alcohols, the preferred mechanism is always E1. E1 is preferred mechanism. Let me show you mechanism how it is with an example. Suppose if you have O and H here, and there is an acidic medium like concentrated H2SO4 or concentrated H3PO4. If you observe carefully, BF3 is also a Lewis acid, THO2 is a Lewis acid, Al2O3 is a Lewis acid, P4O10 is a Lewis acid. So basically any acid group you need to have, correct? So I can take either H plus or I can take even BF3 also. The point is the lone pair will definitely attack on the proton here. So as it attacks, it will go through a formation of this ion. O, H was already there, one more H has come with positive charge. Got it. And it has one lone pair also. This is called oxonium ion. Oxonium ion. Now from oxonium ion, the reaction will slowly, you can see, slowly H2O will depart this way. OH2 will depart from here. So then what do we have? We will get the carbocation here. There is a proton here at the beta position. So water solvent, which is a solvent, as a base, extract the proton and try to make it as a double bond. So from here you will see the product formation will be alkene. So this is the general mechanism of dehydration. Okay, students. Now, in case of when does this carbocation usually forms? Carbocation usually forms when it is 2 degree or 3 degree. If it is 1 degree, direct reaction will take place, which means H2O will attack here. This OH2 will leave from there. And if you see the reaction progress curve, how it is, we started from here, alcohols. So from here, first it has reached to an intermediate, which is oxonium ion. From oxonium ion, it is a slow step. Sorry, made a mistake. From here, let's say, from here, it has gone through this and reached to an oxonium ion. Why oxonium ion is coming down? There is an extra sigma bond. Please understand that there is an extra sigma bond here, because of which energy will come down. And from there, it is going to a height and finally forming a carbocation. So from carbocation, elimination is taking place and finally product is forming. So this is the carbocation formation, this is an oxonium formation, this is alcohol, and this is alkene. This you have to mug up because this only comes from an experimental data. Okay, students. So the first one, THO2, when it comes to thorium dioxide, Hoffman is always major. Al2O3 and pyridine. Al2O3 and pyridine. Okay. We'll always get Shazef. Al2O3 pyridine. we'll get Shazaf. But one important thing is without rearrangement. Here everyone. Next, all other dehydrating agents. So you have to mug up these three students. Only THO2, Hoffman, Al2O3 pyridine without rearrangement, and rest all will be regular mechanism, which is Shazaf with rearrangement. Let me show you one example here. Suppose if we have OH and I treat that with H plus heat. So first there would be formation of carbocation here, right? That carbocation will rearrange by 1,2 hydride shift. So which means H from here is shifting here. So which makes it to form this carbocation. So from this carbocation, we can have many products. So what are those? We can get double bond here, plus we can get double bond here. Got it. And one more thing we are forgetting is that before rearrangement. So before rearrangement, also it can undergo double bond formation. Here, this will have cis plus trans. This will have only one product. This is also one product. So total how many products? Total 4 products.
Sir, without rearrangement, another product could also form, no, sir?
Without rearrangement, it is the same one. Huh? This is the same one which you will get. Cis or trans.
Okay.
So I've included that here only. Because if we have this way, it is treated with H plus. What do we get? First, we'll get carbocation here. So from here, I'm directly writing the product before rearrangement. Product number 1. Then rearrangement. Right. I'm taking all the possible ones. This can be possible. So from here, I can get one more product like this. And another product which I can get is this one. This is another possibility. Now from here, ring expansion. So with ring expansion, we will get this 6-membered ring with positive charge. And that will lead to this product. Got it? If you are asked what is the major, then this is the major product. If you ask total number of products, how many products beta? 3 of them. So as soon as the carbocation is formed, before rearrangement, I can have this product. Double bond here and this one. This is one product. Next, by rearrangement. How does the rearrangement happen? Ring expansion. So the ring can expand. The ring can expand here. We can have this, right, with carbocation forming here. So this will give how many products? Another cyclopentine with OH on it. OH is present here. So with H plus and heat, first what do we get? We get a carbocation here, and before even making any expansion, we can get, that's it, these two products you can get before rearrangement. Now how does the rearrangement take place? That is by ring expansion. So by ring expansion, we can have this as the 5-membered ring connected to the 6-membered ring. This way we can get an alkene here. Sorry, on this side we can get one alkene. Or again there would be ring expansion. Again, if the ring expansion takes place, we would get this as, this way we'll have ring expansion with carbocation, and from here we will have an alkene. I hope all of you are done. These are the products you will check.
Sir, once show the B example, sir, second one.
Now come to the next point here. We have been discussing more about the substituted alcohols only. What if you have primary alcohols? So primary N-alkyl alcohols, they also undergo dehydration, but by E2 mechanism. Okay. They form most stable among the possible alkene, which is actually explained by reversibility of dehydration. Is explained by dehydration. Let me show you example what it meant. Suppose if at all I take this butanol, get rid that with H plus and heat. Well, I'm expecting a double bond formation here and then double bond formation here plus a double bond formation with cis and trans. These three are expected ones. Here. Now, when you have this OH2 plus forming, right, and we have H here, so what would happen? H2O will try to extract this proton, pushing this bond and remove this OH2. When you do that, minus H2O heat, you would get this as a double bond here, and H3O plus has been formed. This remains. Now, where is the reversibility coming? You can see this pi bond which is formed here, that would react once again with H plus, and forms a carbocation here, and then gives this double bond formation and double bond formation this way. Suppose in case if we have OH this one, and I gave you various compounds, various reagents, you just have to remember, we just have to work out what should be the product that you can get. First with H2SO4, next with Al2O3 and heat until undergo ring expansion. Finally, carbocation will come here, and from there alkane will form. So this will be the final product. Al2O3. Al2O3 will also give Shazef as the major product with rearrangement, which means all the similar steps will happen with Al2O3 also, and finally you'll get this product. Now, what did I tell you about Al2O3 with pyridine? With pyridine, it is still going to give Shazef, but without. Very good. So, since it is without rearrangement, where does that double bond form? It form here. So, with the double bond form. Last one, THO2. Where does the double bond form? It is Hoffman being major product. So, double bond will be at this terminal. Here, everyone, Shazef plus rearrangement. Shazef plus rearrangement.